Okay, so here's our first sample problem for the specific energy in open channels. The problem is taken from the textbook by Hibbeler, and it's example 12.1. It says that water has a velocity of 4 meters per second as it flows along the rectangular channel shown in the figure. If the depth of the flow is 3 meters, classify the flow. What is the velocity of the flow at that alternate depth that provides the same specific energy for the flow? So here's our rectangular cross section, and the depth is 3 meters and 2 meters, and we have this a flow velocity of 4 meters per second, and we are asked to classify the flow, whether it's in subcritical region or supercritical region, and also we are asked to provide the alternate depth for that same specific energy for the flow. Okay, so for the solution, so in order to classify the flow, then we have to solve first for the critical depth. Right, so to classify the flow, solve first for the critical depth, y c sub r. Okay, so our equation is q squared t all over g a cube is equal to 1, and our a, recall that a is just simply the width, this width times the depth. So y sub c, of course, we are evaluating, we are solving for the y sub cr, so we are not going to use this 3 meters. And also for the top width, since this is a rectangular channel, then the bottom width is just equal to the top width. It's just equal to 2 meters. Okay, so if we substitute all the values here to this equation, what we get is q squared times t, that's just simply b, and g times the a, let's just write it this way, b cubed times the y critical cube, right, is equal to 1. Okay, so let's isolate this y sub ycr to the right hand side. What we get is q squared times b. Take note, we have b here, and we have a b raised to 3 here, so therefore it's just g times b squared is just equal to y c sub r raised to 3. Okay, so if we substitute the values, recall also that the q is just simply the area, that's 3 times 2, that's the flow rate, 3 times 2 times the velocity, right, times velocity, which is 4, and we square this, divided by 9.81 times the b, which is just 2 squared, and this is yc sub r, and this is cube root. Okay, so 3 times 2 times 4 squared divided by 9.81 times 4, and we take the cube root. This is 2.45. ycr is equal to 2.45 meters. Okay, so here's our critical depth, and the depth in this condition is 3 meters. So y is greater than ycr, and therefore the flow is subcritical. So drawing now the specific energy diagram, we have this. Alright, so here's the y critical. This is 2.45, and our depth is this. This is y is equal to 3 meters. And the next thing that we are going to solve is the depth right here, right? So what's going to be the y right here at the supercritical region? So take note that this curve is a constant flow rate. That's q is constant, right? So meaning that the flow rate right here at this depth is the same flow rate at this depth, and also that's the same the specific energy at this point is also the same specific energy at this point. So in order to solve for the y right here, we solve first for the specific energy at this point. Okay, so solving now for the specific energy at y is equal to 3 meters. So E is equal to y plus v squared all over 2g. And at 3 meters, our y is 3 plus v squared. That's just 4 squared, right, divided by 2 times 9.81. 3 plus 4 squared. So this is 4 squared divided by 2 times 9.81. Okay, plus 3. That's 3.815. Okay, that's in terms of head. Okay, so now solving now for the alternate depth. Right, so we use the same equation, E is equal to y, except that this y is the y at the alternate depth. So this is unknown, this is given, this is unknown, plus, and right here instead of using the v squared all over 2g, we'll use this other term, q squared is equal to 2g times what's this, times a squared. Okay, because this one is constant and this one can be expressed in terms of the depth. So let's do that. What we get here is E is equal to 3.815, and our y, that's the unknown, plus q squared. So our q is just simply it's simply area times velocity. So 3 times 2 times 4, 3 times 2 times 4, so that's 24. So this is 24 squared all over 2 times 9.81 times the b squared, right, because this is b times y. So our b squared is 2 squared times y squared. Right, so in this equation, the only unknowns that we have is the y. Okay, so let's simplify first the constants here. So 3.815 is equal to y plus 24 squared divided by 2 times 9.81 times 4. And this is 7.34 divided by y squared. Okay, so now let's arrange the terms because this will be a cubic function. So let's multiply the equation by y squared. So that's going to be 3.815 y squared. So y squared times y, that's going to be y cubed, plus this one would be 7.34. Okay, so let's arrange this in, because to solve that we have here in our calculator. So mode and equation, this is 5, so press 5. Okay, so right here we have a function like, for example, if we have x and y, and here's our constant, and what if we have x, y, and z? It's a linear, but x, y, and z. Right here, if we have a quadratic equation, x squared, x, and a constant, and right here we have cubic functions, so x cubed, x squared, x, and a constant. So the a, b, c, and d, they are the constants, and the x cubed, x squared, and x, they are the that's our variable. So we will arrange this equation in this arrangement. So first, that's gonna be y cubed plus, we have to transpose this into the left hand side. This will be minus 3.815 y squared, right, plus our cx or y, right, cy, so that's 0 because we don't have any, plus 0. Okay, plus our constant of 7.34. 7.34, this is equal to 0, right? So let us write down our constants. So our a is equal to 1, our b is equal to negative 3.815, our c is 0, and our d is 7.34. So here it is. Here's our equation, and the right hand side should be 0, right? So let's select this. So again, from so here's our default, and now click this mode and click number 5 and press 4 because that's the cubic functions. Then let's input the value of a, b, c, and d. So our a is 1, our b is negative 3.815, our c is 0, and our d is 7.34. Right, so that's it, and then just press equals. Just press equals, and it says here that our y sub 1 is because this is a cubic equation, that means that we will get 3 values of y. So the first value of y is negative 1.21, and just press equals again. For the second value, this is y, our y sub 2 is 3, and the next the third value is 2.02, so y sub 3 is 2.02, right? That's in meter. So this is not real, so that's not it. And this one, this second y value, that's our first depth, that's 3 meters, and here's gonna be our alternate depth. So therefore the alternate depth for the same specific energy is y is equal to 2.02 meters. Okay, so lastly, don't forget to write the summary. So in summary, so here it is. Here's our depth, and here's our specific energy, and here's our asymptote, and right here, here's our constant flow rate curve, and this is 2.45. This one is, let's say this is 3, and the alternate depth is this, right? So this is 3 meters, and this one is 2.02, and therefore this is in supercritical, of course, supercritical region, and our specific energy is 3.815 meters. Okay, so that's it. Now let's do another problem regarding this specific energy. Here's our second problem for this topic in specific energy. This one is taken from the textbook by Potter et al. Entitled Mechanics of Fluids, and specifically this is example 10.3. The problem says that water is flowing in a triangular channel with t is equal to 1. That's the side slope, and it has a discharge of 3 cubic meters per second. If the water depth is 2.5 meters, determine the specific energy, the flow number, the hydraulic depth, and the alternate depth. So here's our channel cross section. It's a triangular in shape, and here's our flow depth y that's given. This is equal to 2.5 meters, and here's our top width, and here's the side slope. Okay, so first let's compute for the area and the top width. So area and top width, the area is, if we go back to our lecture materials, here's our triangular cross section, and the area is just simply the horizontal portion of this top width, of the side slope, and the y squared, that's the flow depth. So A is equal to t times y squared. So t is equal to 1 and y is equal to 2.5 squared, and therefore this is 2.5 squared. This is 6.25. So 6.25 square meters, and then for the top width, this is 2 times t times y. So 2ty. So 2 times 1 times 2.5, this is 5.0. So therefore we have here, this is 2.5, and right here this is 5.0, and this is 1. T is equal to 1. Okay, so now let's solve for the specific energy. Solving now for the specific energy. So this is E is equal to y plus, I'll use this q squared all over 2g times a squared. So y is equal to 2.5. The flow rate is 3 squared. This is 2g times the value of area, which is 6.25. So this is 2 times 9.81 times 6.25, and that's also squared. So 3 squared divided by 2 times 9.81 times 6.25 squared. This plus 2.5. This is 2.51. So 2.51 meters. Okay, so what else? Specific energy, the flow number, the hydraulic depth, and the alternate depth. So I guess we can solve for the alternate depth at this section, or at this given condition. So E, the same value is equal to y, except that for the alternate depth, that's our unknown. So let's just write y. Y plus, what else? Y plus q squared. Q squared, let's write here, q squared all over 2g times the area. But the area is just t times, this is it, t times y squared. This is 1. So what's left is just y squared, right? And don't forget the square of this term. So that's going to be y to the 4th. Alright, so let's substitute this. 2.51 is equal to y, because we are solving for the alternate depth. Let's write here, solve now for the alternate depth. Alternate depth. Okay, so q squared, this is 3 squared divided by 2 times 9.81 times y squared, that's y to the 4th. So let's simplify this. 2.51 is equal to y plus 3 squared divided by 2 times 9.81. This is 0.458 or 459, 0.459, and this is y to the fourth. Okay, so let's multiply this equation by y to the fourth. So this is 2.51. Y to the fourth is equal to y to the fourth times y, that's y to the 5 plus 0.459. Okay, so let's rearrange this. Y to the 5 minus 2.51 y to the fourth plus 0.459, right, is equal to 0. So that's our equation, but this is no longer a cubic equation because we have a degree of 5 in our variable. So if you use this calculator, we can only have up to the maximum of a cubic equation. Okay, so we can we'll use this calculator, another calculator of mine, and this is a graphing calculator. This is Casio FX9750G. So we'll try this. Right, so here's our equation. So this is number 8. So I'll press 8, and I'm going to select a polynomial. So that's f2, and it asks here what's the degree, and since I have a 5th-degree equation, then I'll choose this 5. Right, so basically what it does is something like what I did here, that we just have to input the value of the constants for each terms, right? So I just have to input that, except that this one has a more capability because it can solve for higher degree equations. So for our a sub 0, that's the a0 x to the 5, and then the a sub 1 would be the constants or the coefficient for the y to the fourth, and so on. So we have 1 minus 2.5 for the second. Right, so let's input this 1, and then minus 2.5, 2.51. And for our cubic term, since we don't have any, that's just 0. For our squared term, that's also 0. And for our first degree term, this is also 0. And this is 0.459. So 0.459. Right, so that's it. So now let's try to solve this. And it gives us a value of y could be equal to 2.51. Right, so this is 2.51, and then we have 0.71. So 2.51, and the other one is 0.71, and the other one is a negative 0.6, negative 0.6. Okay, so that's it. Right, so basically, if we have these functions and we are to solve for this unknown, for this y, of course we can always use the basic mathematics rules, or we can just use softwares if we want a faster solution. Alright, so that's it. So this one is not possible. This is negative 0.6, and this 2.51, that's the flow depth close to this one, and most likely this is it. And the other or the alternate depth would be 0.71. So therefore the alternate depth is 0.71 meters. Right, so this one is already solved, and this specific energy is already solved. So now let's solve for the Froude number and the hydraulic depth. So step 4, solving now for the Froude number. Right, so FR is equal to V divided by square root of G. What is this? 2G times this flow depth, right? So V, that's from our flow rate equations. Q is equal to AB. We have the Q, we have the V. We have the Q, we have the area. So therefore, we can solve for the V. So this is just simply 3. Right, so this is 3. That's the flow rate Q divided by the area of 6.25. Right, divided by the square root of 2 times 9.81 times the flow depth. So the flow depth is, of course, the flow depth of this given flow depth, that's 2.5 meters. So this is 2.5. And now let's compute this. Right, so 3 divided by 6.25 divided by square root of 2 times 9.81 times 2.5. This is 0.07, or let me check again. So 3 divided by 6.25 divided by square root of 2 times 9.81 times 2.5. This is right here, 0.07. So that means that FR is less than 1, and therefore the flow is subcritical. Right, so for the hydraulic depth, recall that the equation for hydraulic depth is just simply the area divided by the top width. So this is 6.25 divided by 5, and this is equal to 1.25 meters. Alright, so lastly, let's draw, in summary, the specific energy diagram is this. And here's our critical depth of, actually we did not solve this, but we have this one, this is 0.71, and the other one is 2.5. .71. Okay, let me check this once again. 3 divided by 6.25 divided by square root of 2 times 9.81 times 2.5. Alright, anyway, that's it. So this is it. So in review, what we did is we just simply once we know the area, or once we know the geometric properties, then we can actually apply the specific energy equation. And from that equation, we know that there's an alternate depth, and to solve for the alternate depth, we just simply use the same equation, but of course we are we are referring to another type of depth, so that would be our unknown, but the flow rate is the same, because from this equation here's the same flow rate, so that means it's the same flow rate whether it's the depth is right here or this one. Okay, so after that, then it just happens that in this type of problem we have a function that's a degree 5, and of course we just need to use a computer or software or maybe a calculator that can solve for this, and then we just simply input the coefficients and then it will give us the answers. So here's our answer, 0.721, and then we are asked to solve for the flow number. We just simply substitute all the equations, and we also solve for the hydraulic depth. Okay, so I guess that's all for our topic in this open channels. Actually, we still haven't discussed, there's still much more computations with regard to this specific energy, because right now what we did was just, for example, here's the channel. What we did is just simply to consider only one section, right? So let's say in this section, of course there's a flowing water, for example. Then at this section, what's going to be the alternate depth or the critical depth? So alternate depth. However, it can also be applied, I mean, this concept in specific energy can also be applied or is useful when there's in solving problems involving transitions. When we say transitions, there's changes in the geometry. So for example, from this width, then it goes to this width, say a rectangular channel, but we have a transitions from a wider width to a narrower width. So what's going to be the depth at this, let's say at this end? So if we look at this elevation view, what we see is something like this, right? It can have a non-uniform profile. Or here's our flow, here's our depth right here, and what's going to be the depth right here. And also the specific energy equation are used, like for example, we have changes along the, instead of having a flat bottom, there's going to be a bump, or there's going to be something that's that will have changes in the bed elevation, right? So we did not discuss this because of time, but anyway, that's I think we have already established our concepts in this specific energy. Okay, last concept that I'll discuss, or actually I'll just mention, is the term hydraulic jump. So this hydraulic jump is basically a phenomenon where from a, for example, we have here a dam, for example, and we have this water that's going here or that's going down here, and then if we are in this critical or supercritical region, we are moving very, very fast, but then right here we are forced, or we are rapidly changing into a subcritical region, and therefore there's actually a jump of this depth right here. So that's what we call the hydraulic jump, and this is actually associated to the energy, because if there's no control for energy, I mean, in that transitions, there's a lot of energy that's dissipating, and it can damage, like probably the soil down here. So it can erode, or it can scar some structures, or scouring of the soil near the structure. So it needs to be controlled. So the concept of hydraulic jump is that the water is from a supercritical, that means a fast moving but shallower depth, and then it changes rapidly into a subcritical region, meaning lower speed, higher speed here, lower speed right here, and we have a higher flow depth, right? So that's the concept of hydraulic jump. All right, so the next In the next video, we'll discuss our next topic, and we'll talk about the external flows.